The first part of the activity today is about Adams Flex, which is the method for introducing flexibility in the multi-body code. Flexibility defined with interface with finite element code, and which change completely the technology of the multi-body analysis. This technology was introduced in 1994. Before that period was not possible to use this kind of technology, and the flexibility was defined using a discrete method, and I will explain it during this preliminary introduction. So let me start. What is the reason we need a flexible multi-body analysis? First of all, because a rigid body model is too high approximation of the reality, and we want to simulate many complex phenomena in which deformation and stress is included during the analysis. The finite element code is good for structural analysis, but is not efficient from computational point of view to simulate a complex mechanism undergoing large displacement in the 3D space, like a vehicle, like a satellite, like an aircraft, like a robot. So we change our multi-body technology in order to introduce flexible body. The idea is the following: instead of discretize a rigid body in many rigid bodies connected by elastic connection, like bushing, like field, like beam, as we did till 1994, we introduce a new component called a flexible body, and in this component we have a model description of flexibility. When we say model description, it means that the flexibility is defined not through a full structural analysis, but through a model analysis, and every mode of vibration is a degree of freedom of the model, and the combination of these modes provides you a very great definition, very accurate definition of the flexibility. But it is valid only in a linear range of deformation. So this technique is not valid when your flexible body has great deformation, displacement, or the behavior becomes nonlinear in terms of change of material characteristics, plastic phenomena, buckling phenomena, etc. What is the idea? You have your mechanism we define with the rigid bodies, and you can decide that one or more flexible bodies, has to become flexible. So this element is defined with its geometry, and it is transferred to a finite element preprocessor. It is defined with a mesh, with elements, with properties, etc., etc. You can provide all the structural analysis you need to validate your component, and then you can run a model analysis of this component in the finite element environment. When you have performed this analysis, the finite element environment creates a file which contains all the data to describe a flexible body. This file is imported into Adams, and in Adams you have a flexible body. You run a multi-body analysis with a flexible body, and at the end of the analysis you can appreciate deformation and stress in the flexible body after a very complex full nonlinear dynamic multibody analysis. What is the reason for using model flexibility? Because many of the application, in many applications, the deformation is small and can be considered in the linear range. So the model analysis is enough to describe the flexibility. The second reason is that when you ask to a finite element user, to a finite element analyst, to run a model analysis to create a file for atoms, the activity for the finite element user is easy, is simple. There is nothing strange for him. So he has no any problem for running this analysis. There is no any effort, and we don't need to change the technology in the finite element code. This was very important because nobody could accept to change his way of working only for creating a body for us, only for creating a flexible body for atoms. So we asked only the finite element user to print the output also in the file for atoms. This was the only request we did. So the interface is very easy. When you have a flexible body, you don't discretize a rigid body in many rigid bodies, but you change rigid bodies in a flexible one. So the mass is distributed on every node of the flexible body, and the mass so is distributed in a very precise way. And there is coupling of inertia because the inertia is defined on every node. When you run a model analysis, for example, you ask for 10 modes, 100 modes, 1000 modes, you know immediately which is the number of degree of freedom you have in the flexible body. 10 modes means 10 degrees of freedom. 100 modes means 100 degree of freedom. So the degree of freedom are controllable. You can compare immediately the numerical analysis with experimental analysis. So you can validate your flexible body using also experimental data. And this is another great advantage because you can believe in the results because the structural analysis can be validated with respect to numerical experimental one. And at the end, if you have 10 modes, so that 10 frequency, for every frequency, for every mode, you can assign a specific damping ratio. So you can also improve the quality of results, defining a precise damping for every frequency in your system. And this is another important numerical aspect. Which is the technology we used for creating a flexible body? The technology is called component mode synthesis. If you search in the finite element notebook or in the finite element textbook or in the help or in the internet, and you search for Craig Bampton, that is two researchers who developed this technique. This technique is called reduction technique. Which is the idea? You have your flexible bodies defined with nodes and elements. So there is a mesh and the property of the element of the mesh. On this mesh, you assign the master nodes or interface nodes in correspondence of connection or applied forces you will define in atoms. I mean, you don't define constraint or loads in the finite element code, absolutely not. You define only the location of a joint or applied force in atoms. So in this case, we have a simple plate, and we decide that in correspondence of every corner of this plate, in atoms, we will create something like joint, like force. So in the finite element code, we define this node as interface nodes. The finite element code perform automatically two types of analysis. First of all, the finite element code automatically attach the boundary nodes to the ground, release one node and apply 6 unit forces to this node, getting 6 deformed situation of your flexible body. So we have 4 nodes, we have 24 different static configuration, deformed configuration. And this information is stored during the analysis, and you have the stiffness matrix and mass matrix stored from this kind of simulation. Next, the finite element code automatically attach the 4 nodes to the ground and evaluate the dynamic modes, that is, evaluate the frequency of vibration of this plate, evaluating the stiffness matrix, the mass matrix, and the frequency of this mode, and store also this information. So we have 2 different groups of information, one for dynamic aspect, one for static aspect. These information are included in a specific reduced stiffness matrix and mass matrix, plus nodes information, geometrical information, mesh information, frequency information, damping information, etc., etc., etc. And at the end of this, automatically, the finite element code perform a so-called orthonormalization analysis only to create a new modal basis more efficient for multi-body analysis. This orthonormalization procedure diagonalizes the stiffness and the mass matrix, providing the same result in terms of deformation and stress when you apply this flexible body in atoms, but with a different model representation. Equivalent results with different model representation, which is much more efficient because the diagonal matrix is much more efficient from a numerical point of view. This sequence of activity of analysis of procedure is automatically performed in the finite element code, clicking a specific analysis. In Nastran, for example, this analysis is Sol 103, typical model analysis. So when you want to have a flexible body in atoms, it is very easy. You create your mesh in Nastran, you select your boundary nodes, you select how many modes you want to evaluate, and click Sol 103. That's all, and you get results for atoms. The advantage of this technique is evident. First of all, as already said, we have the full control about the number of degree of freedom of...
Excuse me. Can you please repeat the steps that we have to follow to get the results?
Yes, I will repeat the steps, but later I will be more precise. In any case, you select the body you want to make flexible. So probably you have a geometry of this body. You usually import this body in a preprocessor, define your mesh, your elements, so your properties, material, etc., etc. On this body, you select nodes in which in atoms you will have connection or applied forces, in this case 4 nodes, and you select Sol 103, that is model analysis. The finite element code automatically perform static model analysis, dynamic model analysis, and orthonormalization procedure to provide a more efficient representation of the results. And I will show all the steps later when I will use an example. Okay? Hello?
Okay, thank you.
Okay. So, first of all, we control the number of degree of freedom. For example, remember the plate I showed you before. We have 4 interface nodes. In every node, we apply, the code automatically apply 6 static analysis. So we have 24 static modes, deformed configuration. We ask 20 modes, dynamic modes. So at the end, we have 20 plus 24 modes in our model, 44 modes. It means our flexible body is defined by 44 degrees of freedom. So we control perfectly the number of the degree of freedom of the model, depending on the number of modes we want to extract and the number of attachment nodes we have in our model. The static is accurate because we evaluate the static deformation. The dynamic is accurate till the frequency of interest. And the great advantage for multi-body analysis is that due to the fact that we don't define the type of joint, the type of force in the finite code, but only the position of the node, in Adams, in correspondence of every attachment node, we have the full freedom to define variable boundary condition. So we can create a spherical joint, or a fixed joint, or a revolute joint, or applied force in one direction, or three forces, or a force with a sinusoidal function, or a force with impact function, etc., etc. So the condition in correspondence of the attachment node are variable, and this is very important for a typical multi-body applications. Another important thing is that we have the precise mass distribution, because in every node we have mass and inertia. How we change the technology? Multi-body code use the so-called Lagrangian formulation, in which we have the dependence of the Lagrange formula from the coordinates of the system. In these coordinates, we introduce also the modal coordinates. In this Lagrange formulation, we have the derivative of the coordinates, and the dependency on the constraints and the applied loads. If we evaluate the deformation of a point in a flexible body, we have the position of the body with respect to the ground, the position of the point with respect to the origin of the body, and the deformation of the point, the deformation of the body. These three components, in these three components, this deformation can be approximated by modal expansion. So it is up to us to decide how many modes we need to describe this deformation. More modes we have, more precise will be our result, but there is, you know, a limit, and you can have very, very accurate results using a good number of modes without the need to use thousands of modes. If you want to evaluate the kinetic energy and the potential energy included in the Lagrange formulation, and to evaluate the velocity and position, you use modes and derivative of the modes. You can see here how the equation are modified by the presence of the modes. And you can see that we have kinetic energy depending on modes and potential energy depending on modes. It means that if we look at the equation of motion, and this is the equation of motion, we have the mass matrix multiply the second derivative of the coordinates, as we have in the rigid body formulation. We have the derivative of the coordinates multiply the damping matrix, as we have in the rigid mechanism. We have the stiffness matrix multiply the coordinates, as we have in a discretized rigid body system. Equation of constraints, equation of loads, but a new element appears, this one, the partial derivative of the mass matrix depending on the coordinates. It means that our mass in the space change its distribution due to the deformation. This component is absolutely new in the Lagrange formulation. It doesn't exist in the rigid body formulation. It means that we need to evaluate at every step time of analysis the variation of the mass matrix depending from the coordinates. It is a very expensive, big effort for the computational, for the solver, but we need to know it, to evaluate it, otherwise we are not able to evaluate the deformation of the system. This is the modification we did in our technology. It is important to know the variation of mass. So, when you have the mass matrix, we can appreciate in the mass matrix terms that depends only from translational rigid coordinates, translational rotational coordinates, or translational and rotational rigid coordinates, and terms that depends on also from the modal coordinates, first order and second order. In this mass matrix, you have to, this mass matrix must be evaluated at every time step. In order to reduce the computational effort, we can first of all find terms that are not changing during the simulation. These terms are called inertia invariants. For example, the total mass of the flexible body doesn't change. The distribution of the mass in the space changes, but not the total mass. And the same for the rigid part of the total moment of inertia. And the same for the rigid static moment. They don't change. So the inertia invariance can be evaluated. These inertia invariants, let me skip some slides.
Just a second, Daniele. Just to mention that what you just showed here, these inertia invariants are what we have already discussed as inertia shape integrals in our course. So you can totally relate to what Daniele is showing here in this slide. In fact, just yesterday we completed an exercise estimating the mass matrix that he is showing right now with all the submatrices. Thanks, Daniel, you can go on.
Okay, thanks. So if we look better in detail the content of the mass matrix, we can see how every component depends from rigid or elastic, let me say, modal coordinates. And we can evaluate these inertia invariants. You see here total mass of the body, inertia invariance number 1, moment of inertia of the body, inertia invariance number 7, first static moment, inertia invariant number 2, mass matrix on every node, inertia invariance number 6, etc. Some of these invariants are not related to the modal coordinates, this one, and this one. Some of them are related to the modal coordinates with the first order of the modal coordinates. You see inertia invariance 3 and 4, for example, and 8. And inertia invariant number 5, 6, and 9 depend on the modal coordinates at the second order. You see here from the equations. So it is evident that if we have a great displacement in the 3D space, in 3D space, plus a small deformation, when deformation is considering also the second order terms, the contribution of the second order term is very small. And in some cases, this contribution is negligible. You can avoid, you can neglect it. And this contribution of the second order modes, it is the contribution which requires more computational effort because you have to evaluate the modes twice. So if we neglect this contribution, we can have a very good result at very high, with a very high efficiency. if you run a simulation in Adams in which you neglect the second order terms, probably you can get results in terms of seconds. When you introduce the second order terms, probably you need twice of the time, sometimes 10 times of the time, sometimes you need hours, depending on the complexity of the simulation. So we introduced the technique to use the invariants in order to decide the level of complexity and accuracy of our flexible model. In many situations, the second order terms can be neglected. In some situations, you cannot neglect. For example, when you have a rotating system at a very high velocity, the second order terms becomes important and you cannot neglect them. When you are working in Adams and you use only invariant 1, 2, and 7, you are using a rigid body. So immediately you can understand that if I don't use 3, 4, 5, 6, 8, and 9, my flexible body behaves like a rigid body. So with one model, I can simulate the rigid body effect and the flexible body effect. Then, if you use invariance 1, 2, 3, 4, 7, 8, we have the so-called partial effect of flexibility with the first order of the modes. If we include also mode 5, 6, and 9, we have second order terms included, and we have the full description of flexibility. We did many activities testing our solution and evaluating results using partial method or full flexible method, and we can say that using partial method is enough for 90% of application, and only in some more small number of applications you need to use the full flexible method. But it is up to you to decide the level of accuracy. You are completely free to decide which invariant you want to activate or deactivate. This gives to the Adams user great advantage because you can perform optimization and debug of your model using a very efficient method, and when you are at the end of your design, you can activate also the other invariants. Which is the way of working? Okay, so we run a finite element model analysis in the finite element code. At the end of this analysis, the output are written in a model neutral file. The name model neutral file means that the data are describe the flexibility with model method, and the neutral means that this file is the same, that is as the same content and format independently from the finite element code you are using. So you can have the same file from Nastran, from Mark, from ANSYS, and from Abacus, for example. When you have this file, you can open Adams View, and you can create a flexible body reading this file. The Adams solver, that is the core of Adams, extract the important information from this file, run the simulation, and at the end, in the post-processor, you can visualize displacement, velocity, acceleration, deformation, velocity of deformation, acceleration of deformation, stress, etc., etc. Interactively, you can create a flexible mechanism with a flexible body or many flexible bodies. You have a dialog box in which you can visualize the model content in terms of numbers, in terms of animation. That is, you can also visualize the model of vibration. You can decide the level of flexibility you want to activate, and there are other things like definition of damping, etc. This is the visualization from a numerical point of view of the content of frequency. This is the inertia table. This is the visualization of the mode of vibration. When you run the simulation, you can appreciate at the end of the simulation that the system behaves with the flexibility. So you see oscillation, you see distribution of deformation, you can see distribution of stress in the flexible body. In a dynamic analysis, fully dynamic analysis, or static plus dynamic analysis, which is not absolutely the same you have in a finite encode, in which the type of simulation is very limited in a small configuration around the starting configuration. In the finite encode, you are not able to simulate long simulation in a 3D space with no limitation, because the technology is different and the target is different. There is also the possibility to perform the creation of flexible body directly into Adams. If using a module called ViewFlex, you have Nastran or part of the Nastran solver in Adams, and you can switch a rigid body to a flexible one without the need to have an external finite encode. The limitation is that in Adams you don't have the full preprocessor you have with Patran or Mentat or other preprocessor, but the preprocessor is limited to the target of Adams, so creation of a flexible body. There are many other pages in the material I sent you, but these pages are only let me say, a deeper description of this technology, so you can read these pages and you can have other information in terms of results. So let me go to the next information about damping. The damping can be introduced directly in Nastran, and there is an interface, some statement to have the damping matrix, or you can apply damping in Adams, and in this case you apply the so-called modal damping, which is a percentage of the critical damping of your structure. The modal damping is a percentage of the critical damping, so this is the critical damping, and you can define a modal damping different for every frequency you have in the flexible body. So if you have 100 modes, you can create 100 damping ratio. You can use the 100 damping ratio in your system. The damping affect the damping matrix. Which is the effect of the damping? You can have no damping, resonance. You can have low level of damping. You can have very high level of damping or critical level of damping, overdamped results. And depending on the damping you use, you change the dynamic content of your system. So you need to know the damping value, or you need to use it carefully without inventing something. So be careful when you assign damping in your system. This is a typical transient analysis in which the results are different depending on the level of damping you use. And here is where you apply the damping. The default value of damping is something that is important because to avoid zero damping. A model with zero damping is not realistic. Every structure in the world has an internal damping. If you have no information, we provide you this kind of representation. So low level of damping when the frequency content is under 100 Hertz. Medium level of damping for frequency between 100 and 1000. Overdamped the situation when the frequency is bigger than 1000 Hertz. But it is absolutely an approximation, a rough, brutal approximation. You can define the low of damping you want, depending on time, depending on frequency, etc., etc. In some cases, some users use advanced subroutine for assign very interesting value of damping. This is an idea of function you can assign for the damping. There are many other things to say. We can apply modal forces, we can apply preload, but we have no time to see these things. You are invited, encouraged if you want to, if you need to do a thesis to improve your knowledge about it, you can ask me or my colleagues more information. Let me go to some examples. How we create how we define a finite element model for in the finite element code for atoms. We have some rules, very simple rules to follow. Let me give you. Okay. First of all, if we use Nastron, the modal analysis is called Sol 103. So this is a very famous analysis already existing in Nastron. So to get an atom's flexible body, you run this analysis. The thing you need to remember when you run this analysis is to define an output card. The output card is the following. I want to get the output in Adam's MNF file. So the results of this analysis will be written in the standard Nastron files, F06, F04, log, XDB, etc., but also in a file called MNF. When you ask for an analysis for atoms, you have to remember to define the node called interface node, and the card to assign the master node, interface node, is called ASET1, and you can use a Lanczos method for evaluating dynamic modes. So in this card, you ask how many dynamic modes you want to get. So it is evident that for a typical finite element user, nothing changed. This analysis is a modal analysis, standard modal analysis. Lanczos method is a typical method for evaluating mode. Assign some nodes require the use of a card like this, which is standard. The only new thing is to remember this card. I want to have the output in the MNF format. Okay? Last information to provide for atoms is the card for units. In this card, we define which are the units of the flexible body: millimeter, Newton, kilogram, etc., etc. So when Adams reads the file, knows the units of the content of the file. When you create a MNF file, before to go to Adams view, it is better to use the Adams Flex interface, which allows you to read and evaluate and comment the content of the MNF file. If you are the creator of the MNF file, probably you know everything. If you get the file from somebody else and you don't know the content, before to apply the content in the Adams model, it is better to see if the content is good. This interface is a sort of debugging activity in which you can read the nodes, the mass matrix, the stiffness matrix, the frequencies, the interface nodes, the mode shape, the damping matrix, etc. If something is not good, it's completely useless to create a flexible body in Adams, because if the MNF file is wrong, Adams cannot do anything. If the MNF file is wrong, you or your colleague in the finite element code did something wrong. Okay, remember the following: never Adams fail with flexible body if the flexible body is made with right information. If Adams fails with a flexible body, default is in the MNF content, which is something that you get from finite element analysis. So when you have a flexible body which doesn't work, you have to go back to the finite element code. This is the Adams Flex with dialog box. So we have the name, the damping, the model content, visualization of the modes, the inertia characteristics. This is the flex, the model content frequency. This is the inertia content activating or deactivating the inertia invariance. Okay, a couple of examples. Let me show you a couple of these examples. I want to show you interesting example. For example, like this. We have our satellite. In our satellite, our flexible body, our solar panels and parabola are made with the flexible bodies. So during the deployment of this solar panel, the flexible body can vibrate, can oscillate because you have deformation, you have structural effect. Due to this vibration and deformation, you can have oscillation in the full system, and the satellite can go out from the right trajectory. So your control system has to be activated in order to recover the right asset, the right height, the right trajectory, okay? So we need to run an analysis not with rigid bodies, but if the movie starts, I guess. I don't know why it doesn't. Okay, it's starting. This is, you see, during the deployment, you see variation of colors. It means variation of deformation and stress along the flexible bodies. This movie is very old. It is a movie of 30 years ago, but the idea is evident. This is a landing gear for drop test or for landing. This vehicle, this aircraft, is made with a flexible body. The representation is sketched for confidentiality purposes, but everything is oscillating and vibrating. So you have a flexible distribution of loads, a distribution of loads on a flexible body with deformation and stress. This is a flap made with the flexible body. During the extraction or retraction of the flap, you have variation of deformation, otherwise an aircraft cannot fly, and you have variation of forces, aerodynamic forces, because the surface change due to the rigid movement, but also to the deformation. You have bending and torsion of this flexible body. Or, for example, you have this truck entering in a hole. So if you want to evaluate the distribution of stress on the flexible frame here, you need to run this analysis, changing the speed, the height of the hole, the radius of the curve, the distribution of the payload on the flexible frame. So in order to improve, to optimize the structural content, you need to run many analyses using flexible body. This is something a truck company is doing with Adams from many years, and they improve the quality of the structural flexible frame. This is an UAV and you have flexible wing, flexible fuselage, flexible aileron, flexible elevator, and you see distribution of forces along the flexible bodies. So during, for example, every kind of flight, you see how the flexible aerodynamic, the aerodynamic forces change value and distribution on vibrating system, and it changed completely the flight of this aircraft. Or in this case, we have a tail rotor of an helicopter. When you have to consider the variation of the content in terms of stiffness matrix and mass matrix during the movement of this tail rotor, you have different region of contact between the bushing and the bearings and the flexible shaft and the flexible hub. You have different frequency in the full system. You can have, in some situation, a coupling effect with the aerodynamic force, and this coupling effect can have a unlucky situation in which everything starts to vibrate too much and the tail rotor is destroyed. So we need to avoid this situation. Or you have a system like this. A satellite is positioned on this plate. There is a mechanism which is able to push the satellite in the space through a spring here, but the energy of the formation of the plate, when the plate is released, contribute to the pushing of the satellite. And if we neglect this energy included in the plate deformed, you are not able to correctly position the satellite in the space. So we need to consider the flexible body here. And there are many other examples. Here we have a landing gear of a famous Italian fighter, and we have many flexible body during the landing and runaway maneuver. We have a contribution of the brake system, which is coupled with the vibration of the flexible body, and everything starts to vibrate too much. Typically a shimmy effect, typically a vibration effect which disturb both handling and durability and noise of the aircraft. And we have many other examples on combustion, on rail, etc., etc. Okay, this is the introduction. What about our model? So in our satellite, we need to start from the model we completed the last time. So we can open Adam's view, we can go to existing model, and in our working directory, we search for the model we performed and saved last time. If you remember, we had a full satellite with rigid bodies. We perform kinematic and dynamic analysis, and in the dynamic analysis we used torsion spring, brake system plus latching system included in this function. I can revisualize the animation of this system in order to review the final result. Okay, now we want to replace the rigid body with flexible body. And we have two options. You can go to the inner panel, modify. Sorry, you can go to the inner panel and select make flexible. you can open this window in which you have import or create new. I show you the create new. Please don't follow me. Please only look my activity. If I click on create new, I open this dialog box. And in this dialog box, I can select how many modes I want to run, which is the mesh refinement for my structural analysis. So I can define a mesh with solid element or shell elements. And then I can define the attachment node. When I select and use this window and I click on OK, but now I don't click on OK, Nastron embedded into Adams is performed. Adams creates a Nastron file using the information in this window. The Nastron file is executed automatically through the Adams Nastron solver. The Nastron solver creates the MNF file, and the MNF file is included in the model, replacing a rigid body with a flexible body. This is called ViewFlex. The advantage of this technique is that you are working only in Adams because Nastron is, let me say, not evident to you. And you can use the full parametric model because you can parameterize the dimension of the mesh, you can parameterize the number of the modes, you can parameterize the material of your component, so you can run a parametric analysis. Which is the disadvantage of this method? Here you have a very simplified group of information. You don't have in front of you a sophisticated preprocessor for finite element analysis. We can create only a model with solid element or shell element, but not combination of them. We cannot assign different density to different portion of the model, etc., etc. So we have a preliminary creation of flexible body, but this is very interesting when you are at the beginning of your activity. Okay. The second method instead is make flexible is the method for importing an existing MNF file. The existing MNF file has been created by a finite element user or from you if you are able to work in a finite element environment. And in the finite element environment, you have Nastron file, for example, Sol 103, number of modes you want to evaluate, the nodes you want to use as master node. In the inner panel, we have two master nodes, one for the connection to the yoke and one for the connection to the outer panel. In the outer panel, we have only one interface node because we have only the connection with the inner panel. The rest of the file contains description of the material, type of element, and nodes. Okay, so the Adams, let me say the Adams part is eigenvalues, interface node, and the statement Adams MNF flex body yes. If you run Nastron using this file, you get these results. A file called inner panel.mnf and outer panel.mnf. I sent you these two files. Please, Michele, can you confirm this? They have this file available. Inner panel.mnf, outer panel.mnf.
I'm checking right now. So Daniele, they do not have it yet in the platform in Microsoft Teams. So if you send them to me, I will upload it right now.
Okay, when you got this file, please let me know, and during this time I explain again the the technology, okay?
All right.
Okay. You should have the file now.
Yeah, I'm checking the email. Okay.
They have to put this file in their working directory.
Mm-hmm. Okay, now the two files that Daniele Cataliani gave me are present in the MSc seminar lecture materials folders in Microsoft Teams. Okay, so if you go in general MSc seminar and lectures material, you will find the two files that Daniele was showing us. So could someone of you guys please confirm that you can find the two files in the path? Okay, they are present. Okay, so they have it. They have them
okay,
now.
Perfect. So if you have this file, the idea is to, again, I repeat, go to the inner panel, go to make flexible, and click on import. It means that this file is already available to you. So here the current part to replace is the inner panel, and in this field I search in my working directory the inner panel.mnf. It is a binary file, so you cannot read the content of this file till you have loaded into Adams. When you load this file, probably you can position moving the body in order to make the body compatible and coherent with the system. In your case, my model is already coherent. You can check the connections in order to see if the nodal here is identical to the marker in the rigid body. When you are satisfied with the result because there is no warning message, error message, etc., you can click on OK, and you can see that the rigid body is replaced with a flexible one. And it is flexible not only because you see a sort of mesh of the system here, but because if you look the model browser, now the inner panel is substituted by inner panel flex. And if you go on the body and click on modify, you open the flexible body modify dialog box, which is different from a rigid body dialog box. In the flexible body dialog box, you can visualize the content in terms of model information, model initial condition. Here we have 22 modes. The first 6, close to 0 of the frequency, are rigid linear body modes, so they are deactivated because Adams uses its non-linear rigid body equations to evaluate the great displacement in the 3D space. If you use this linear description, also the displacement are linear, and you don't are using a multi-body code, you are using another type of solution. So these modes must be deactivated. The rest of the modes are activated, and they go from small level of frequency to very high level of frequency. And all these modes are important and fundamental. You cannot remove these modes due to the model content, because they are activated more or less depending on the boundary condition. If you have a fixed joint, all the modes participate. If you have a spherical joint, all the modes participate, probably some of them with negligible contribution. If you have applied force, all the modes participate, probably with negligible contribution. If you don't have any connection, every mode participate, probably all of them with a negligible contribution. But you cannot remove from your ideas this mode. Otherwise, you make a very big mistake. So this mode can be manipulated and investigated after the analysis using participation method or energy investigation method, and only after the analysis you can decide which mode are very important and which can be deactivated, not before the analysis. I emphasize this point because usually if somebody has not understood this technology, if thinks that this mode is bigger than 1000 Hz, I don't need it. No, completely wrong. This high level of frequency is important because you have joint here, and the joint activate high level of frequency. This is the numerical information. Regarding the visualization, you can use this part of the dialog box. If you click 7, means the first flexible mode, enter, and you can appreciate the mode shape amplified. It is a mode shape representation. It is not a deformation. It is, you know, the model analysis. So you can see the mode shape representation. You can animate the mode shape representation. First bending mode, first torsion mode, second bending mode, second torsion mode, etc., etc. So you can visualize and emphasize the mod shape, and all of them contributes to the total deformation of the system. Here you have the inertia modeling description. So if you want to deactivate the flexible content, you can select rigid. If you want to use the inertia invariance depending on the first order of the modes, you use partial coupling. If you want to use all the invariants, you use full coupling method. The default is partial. Regarding damping, if you use the default, it means small level of damping for mode till 100 Hz, medium level of damping till 1000 Hz, overdamped over 1000 Hz. If you want to define your damping level, deactivate default, and here you can write a value constant for every mode or a function depending on frequency, etc., etc., and you can use the law you want. For this example, we can use default. There are many other things to say, but this is enough for this training. We can repeat the same for the second body, the outer panel. So go to outer panel, make flexible, import, verify you are working on the outer panel, search for the outer panel I sent you, verify the connections, click on OK, and now you have the second flexible body. And also on this second flexible body, you can appreciate the model content and the model representation. Okay. First bending mode, first torsion mode, etc. Okay, now if we run a simulation using the flexible body model, simulation, analysis, 5 second, 500 steps, we will appreciate during the analysis and after the analysis that we have deformation and stresses evaluated in correspondence every node of the system. You see, colored map show you deformation and stress of the model. And you have this information in terms of animation, which is, let me say, interesting from qualitative point of view, but it's important to have this information by numerical point of view. So save, please, this analysis with the name Flex analysis, and go to the post-processor. Sorry, I had a problem with my computer. Give me a second, please. Okay. Sorry, I have a problem on my platform. Sorry, 1 second. Today my PC. Okay. Now I can visualize results when I have a flexible body as the same result with some differences I had with the rigid body model. But the interesting thing when you have a flexible body is the following. If you go to results here and you search for flexible body component, inner panel or outer panel, you see that you can print and plot rigid displacement of the rigid part. Sorry, you can visualize the total displacement of the body, including the rigid and the deformation, X, Y, Z of a body, for example, this one. But you can also plot the modal contribution of every mode to the deformation of the body. And you can appreciate that we have 22 modes, for example. We have the possibility to visualize which is the mode which has the bigger contribution to the deformation. So we see that mode number 7 and mode number 8 has important contribution with respect mode number 9 and mode number 10, which has a small contribution, but not negligible, because if you look other modes, also mode number 11 is important. And if we see other modes, we have other, like mode number 15 is important. So it is difficult before is impossible, not difficult, before the analysis to see which modes are important or not. Every of them participate to the total deformation of the system. And only investigating the participation of every mode, we can discriminate if some of them are negligible or not. For example, mode number 20 or mode number 22 has a contribution of 2 orders less than mode number 7. So probably mode number 22 in this analysis can be neglected. But if we change analysis, probably it participates a lot. And in this result file, we have also the first derivative of the mode and the second derivative of the mode. So we can appreciate how the mode change in the time and how the rate of the change again in the time. So we can completely understand how the system behaves due to the flexible behavior. And this is something that only a multi-body analysis can provide you, because a finite element code usually cannot perform this kind of long simulation in time. Okay? This is one of the results. Another interesting result is that if you evaluate in the finite element model the, for example, the characteristic of a marker. So if you select, for example, a marker in the model, flexible body, you can see displacement of the marker, but also deformation of the marker. And this is very important in order to numerically evaluate the deformation of the system. So you can see graphically by colored map of the deformation, but also numerically because you see here the deformation, and you have also the deformation, velocity of deformation and acceleration of deformation. So you have the full dynamic content in terms of deformation, but it is not enough.
May I ask a question?
Yeah.
So normally for when we're using the software, we'll run it for a shorter time and see which of the modes are important and which are not. Is that the case?
No, you run the model for the full simulation, not for the shorter time. You need to run the model for the full simulation, and only at the end of every analysis, you can see, okay, this mode is not important or not, or contribute partially to the total deformation. But if you make a shorter analysis, you have the full understanding of the model.
Okay.
Okay. So another interesting thing is the following. Go to Tools, Plugin Manager. Tools, Plugin Manager. If you click on Tools, Plugin Manager, you can open other module of Adams for performing mechatronic analysis, Adams controls, machinery analysis with the gears, cables, etc., vibration analysis with the frequency solver, and durability analysis for strain and stress evaluation in Adams on flexible body. This is our case. We want to compute stresses on our model. So click on yes, click on OK, and now you see here a durability menu. Under the durability menu, you can see how to work with Adams and finite element code to export data from Adams to this code. This is not our case. How to evaluate stress in our flexible body, maximum value of stress, or history plot of the stress. First of all, we want to see the maximum value of stress in our flexible body. So durability, hot spot table. In this dialog box, you can click the flexible body you want to investigate, inner panel. You can select the analysis you want to use for your investigation, the last analysis with flexible body, and the type of investigation you want to perform. Stress for von Mises, stress normal, shear, maximum principal, etc. Stress, von Mises stress, you know, is a sort of general information about the content of stress in your flexible body. Is one of the more exhaustive method to evaluating stress. And you can ask to print the results in HTML format or in a file. How many information you want to print, for example, the first 10 notes. And if you want to save this result on view, on a window, or in a file. If you click on report, you see that we have 10 hotspot information, 10 values of maximum stress from the maximum to this, which is the node in our flexible body in which we have this value of stress, at which time we got these results, probably when the system activates the latching mechanism, and which is the position in the mesh of this node. So this is a nodal information of stress. Position of the node, time, identification of the node, and value of stress. It is important to know the maximum value of stress, but it is important also to know how the stress is, which is the evolution of the stress during the full simulation, because probably you can have other important instant in which you have high level of stress. To do it, go to durability, go to nodal plots, and in this dialog box, for the last run for the inner panel, you create plots considering, for example, node 4524, the first, and then node 472, the second, etc., etc. You can write in this list all the nodes you want to investigate. You can ask all the information you want to print. So I activate all this information and I click on OK. Now, if you go on results, we have also the inner panel stress, not only the inner panel deformation, but the inner panel stress. And if you create stress, sorry, if you select the stress of the node, you can see the history of stress during the analysis. And if you remember the modal participation, it is evident that we have this kind of behavior considering how the mode participate to the deformation. Okay? So this is the von Mises stress, but we can also have normal X stress, Y, Z, shear, etc., etc. As final information about it, we can switch to animation. We can load the stress, the analysis with flexible bodies. Okay. Now, if I go to contour plots here, instead of deformation, which is the current visualization I can see in the movie, I can ask for stress. Here I have the legend of the stress value, and during the animation I can visualize the region of stress. You see here how the stress change. This is a distribution of stress in our flexible body with a colored map. For a stress analyst, this is important because immediately can understand which are the region in which you can have problem. As final information on this, you can click on hotspot and you can display the node with the maximum value of stress. So you see here the node in which you have maximum level of stress. Nodal stress. So we have deformation and stress during the flexible multibody analysis. Okay, that's all for the satellite. Sorry, that's all for this part of the model in which we have included the flexible body. Any question on this?
All clear, guys?
So
my
earlier question was to trying to understand if we know that after say 10,000 cycles the material behavior or viscosity changes, can we model that into the simulation?
Yeah, you can model damping viscous behavior, changing damping here. Okay. Using a constant value or using a function.
Okay.
If you need to change something else like material, you have to go back to the finite element code, change the material, and recreate a math file.
Okay, so we have to go back to the beginning and completely.
Yeah, because you cannot change the content of flexible body during the simulation using the model method. When you use the model method, the data are evaluated at one time and you use this data for the rest of the analysis. Only the damping is changed.
Yes, that makes sense.
If you want to change the content of the material, you need to use another technique of analysis called co-simulation, in which Adams and Mark or Adams and Nastran are working together, but it is much more complex in terms of modelization. No, sorry, it is a little bit complex in terms of modelization and require more computational effort because you have two solvers working in parallel. It's okay?
Yes, that's okay. Okay. So I have one question regarding the last class. So I was trying to do it again on my own as well. What was not clear to me is how we got the coefficients from the graphs.
Okay. I approximate the coefficient of torsion spring considering the gradient of the curve. So I evaluate approximately the stiffness from the graph and in the linear range, but it's an approximation only for methodology. It is not very precise.
Okay.
I get the graph and I evaluate, let me say, the tangent, okay?
Okay.
Okay.
Any additional question? Okay, I think you can go on, Daniele.
Okay. There is another thing I want to show you is the application of a control system to this model. We have two ways for applying a control system. One using only Adams elements, and the second one using Adams controls, which gives you the possibility to work, for example, in combination with MATLAB Simulink. Today we have time only for the first modelization, but if somebody of you will like to do a thesis on this stuff, for sure I will teach also the other approach. Okay, so and it is used a lot in every industry, principally, especially in a space industry, to control the launcher, the satellite asset, the lander, the rover, etc. So, first of all, go to the chassis here, select chassis measure, and create the chassis measure of movement along X in the space, along Y in the space, and along Z in the space. Due to the fact that we have a fixed joint here, so the satellite at the moment is fixed to the ground, there is no movement of the center of mass of the chassis. But if we remove or deactivate the fixed joint, so the joint now is deactivated, so is in the model but is not active, and I rerun a simulation, I will appreciate that the chassis oscillates due to the fact that the solar panel are displaying and there is also vibration in the system. So this is the X, Y, and Z of the center of mass. If you perform an animation visualizing the trajectory of the center of mass of the chassis, you can also appreciate that there is a movement in the space. Okay, this is the trajectory of the center of mass of my of my chassis. I want to avoid this, or I want to reduce this problem. This for me is an error. I want to maintain a trajectory fixed. I don't want to see 25 millimeters of movement in X or 5 millimeters of movement in Y. Okay, along Z is negligible. Okay, very small. So I needed to consider a control system able to reduce this error. This is an error in displacement. This is considered an error in displacement along X, Y, and Z. To do it, I can use a so-called proportional derivative integral controller. The proportional controller controls the displacement. The derivative controller controls the derivative of the displacement, which is the velocity, and the integral controller controls the integral of the displacement of the error. So we need to create a differential equations for doing it. In order to make things easy, I want to use only a proportional controller. So I monitor and control only displacement, not the velocity, not the integral of the displacement. So I go to forces. I go to vector forces because we need to control X, Y, and Z direction of the satellite. So we need to apply three forces, X, Y, Z. This is a vector forces. The vector forces is not normal to grid, but will be defined using peak feature. And it is not like a bushing, but will be defined with a custom function written by me. The control forces will be applied on the chassis, reacting with respect to ground, that is the space, the universe, and will be applied in correspondence of the center of mass of the chassis. X direction, Y direction. You see here, a vector force is defined by an icon with 3 arrows. And you have 3 functions here, one for the X direction, one for the Y direction, one for the Z direction. In this function, you create your control system. For the X, I select the measure of the chassis along X, and I multiply this measure for example, a gain equal -1000. In my control system, I have to tune, to calibrate this gain. This is a typical function to reduce the error along X proportional controller. The same for the Y. The same for Z. In a perfect controller system, you control also the rotation of the satellite, because in the real analysis you have also spinning, you have also rolling, pitching, yawing of your satellite. So you have also to control a rotation around X, Y, and Z. So these are a very simple control system. Very, 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 very simple. Now, if I run the same analysis with the inclusion of a control system, I will appreciate that the satellite has oscillation, but limited oscillation. You see, I haven't not created a fixed joint, but the control system is able to maintain the satellite close to the original position. And I can also reduce this oscillation if I introduce the derivative of the controller for derivative function, velocity, and for the integral. And this is a typical control force I can control system I can introduce in Adams. There is the possibility to make this in combination with Model Simulink. And if somebody of you would like to know better about this technology, I have an exercise ready for you, and I can send you this exercise. You can improve your knowledge about this, but for today is enough. Okay, in this way I have completed my training, my lesson. What is the project I am preparing with Professor Pasquali for you? The idea is that you will have this let me open it. You will have a payload like this. Okay, this is the payload. You will have a launcher defined with a very simplified geometry, the chamber of a launcher. From this chamber, you will have a spring and a system to release this system in the space while the launcher is moving and rotating as in the real situation. Considering the problem of releasing, you have the need to design this release system in terms of force, thrust, control forces. I will give you many information on this, so you don't have to invent everything from scratch. Part of the model will be available for you, and you have to find the strategy for releasing this system in the space. The idea is that you can use rigid body only in order to avoid the complexity of the flexibility, and to use function similar, not identical, but similar, of the function we have used together for the satellite. Looking for displacement, velocity, acceleration of this system, and avoiding problem of interferences, for example, with the chamber wall of the launcher. This file, this model will be ready for next week, because I am completing it and I'm writing the document in order to give you all the information and to avoid that this problem is not clear, okay, when I give you this model. So probably for the next week you will have, no, probably for sure for the next week you will have this model. I send you the geometry, preliminary model, and a PDF file containing the description of the project. As outcome of the project, you will send me your final model, command file of your final model, in which you will have created your strategy and parameterization, etc., and a report describing the model, the objective of the model, the strategy of your design, and commenting all the result you will present: plots, report, plots, table, animation. This report can be written in Word document, PDF document, PowerPoint document. The important thing is that it must be an engineering report, so everything must be justified, everything must be commented. I will provide my evaluation, not a vote, not a number, but evaluation to Professor Pasquali, and it is now he can explain how he can use my evaluation for the final vote. Okay, but again, I am available for you if you have questions during your project. The only thing I don't know at the moment, and we can ask together to Professor Pasquali, which is the delivery date of this project. Okay, Michele, it's up to you.
Okay, thank you, Daniele. So first of all, I would ask you, Daniele, to maybe write down in the chat your email address that the students can use to contact you already. And so regarding the date of completion, so by which you have to deliver this assignment, the idea is for you to have it completed at least, I would say, 10 days, or, well, I would say, yeah, even 2 weeks or before the date of the exam. So but this we can discuss and it will be made clear in the next lecture. So to give time to Daniele to evaluate these without being in a rush, but to make them in any case available for evaluation in time. That's all from my side. Actually, Daniele, I would ask you one question. Do you think that it would be possible for the students to form groups, to work in teams?
Yes, absolutely. This is typical. Yes, it's important also to know how to collaborate each other.
Mm-hmm. So I would say that given the numbers, I would say that groups of up to, I would say, so I see 13 people. I would say 3. Yeah, but then there are other 2 people outside. So I would say up to 3. So I would say three persons per group. Okay, you can group and you can deliver your assignment working together. Yeah, you can form by yourself. You can form by yourself your groups. You can communicate them to me, and then you will proceed with the assignment. And regarding the material, Daniel, you can send them to me, and then I will make them available for everyone on this platform.
Sure, and this is the first assignment on this kind of project. So I will try to be absolutely complete in my explanation, but if something has to be tuned, I apologize from now, but probably we can make it perfect during the next days.
No problem. It's fine. Okay, we have a few minutes left. Maybe Daniel, you can use them to present the seminar you were talking to me last time.
Perfect. Okay. So thank you for this. Every year, from 5 years now, we are organizing together with La Sapienza Aerospace Department some seminars in order to improve your competence about technology, your competence about industry trends, your competence and knowledge about, for example, skills required by industry. For the next 6th of June, in one day, morning and afternoon, we have organized 2 seminars. The first in the morning is based on additive manufacturing. So you will find it is they are in Italian. So for many reasons we have this seminar in Italian, but all the material is in English. So and the additive manufacturing seminar is based on methodology and simulation tools used by industry and academia for simulating additive manufacturing for metals and plastic material, considering also optimization of the model, considering also validation of the product with many case studies and with some overview about the application in the aerospace industries from 9 to 13. You can find all information in the website on the focus group of Consiglio d'Area di Ingegneria Aerospaziale. This seminar gives you 1 CFU. If you attend, you get 1 CFU. The second seminar in the afternoon gives you an overview about the requirement from the industry, about the role of the new engineer. So what the aerospace industry are searching, which is the mission and the role and responsibility of an engineer in this kind of industry, which are the objectives, how the industry works for the design, how to work in team, which is the schedule time, etc., etc. And this is from 2 p.m. to 6 p.m. in the afternoon in a different room with respect to the morning. The morning is Aula 5, San Pietro in Vincoli, in the afternoon, Aula 22. Again, you can register and attend this seminar. Another CFU available for you. I am preparing also for September another seminar called Tools and Methodologies for Design, and there is a full day based on Adams, Nastran, CFD, controls. You have the full overview about how to make a design from the basic idea to validation. And I have no idea about, I don't know the date, but you will find, if you want, information in the Consiglio d'Area di Ingegneria Spaziale website. Thank you, Michele, that's all.
Okay, thanks a lot, Daniele, for all this nice information. I think everyone will profit of this occasion. So this is all for today's lecture, and I wish you all a nice weekend. So we will see each other on Monday.
Can I ask a quick question to Mr. Catalani?
Yeah.
We are kind of late. I'm sorry, because there is a colleague of mine which is waiting to take the room.
Can you write me?
I can write to you.
Yeah,
okay.
Please write to Daniele Catalani privately. Okay.
Yes. Thank you.
Thanks a lot.